In 1838, Isambard Kingdom Brunel set 3,000 men to work, cutting a trench through a hill east of Reading. The hill was not large. The gradient it presented to the Great Western Railway's planned route between London, Bristol was not, by the standards of the terrain to the west, exceptional. But Brunel had decided that his railway would not climb hills, it would go through them. The trench that resulted runs for 2 miles, reaches 60 feet in depth at its deepest point, and required the removal of approximately 3 million cubic yards of earth and clay, all of it moved by hand, by wheelbarrow, by horse-drawn cart, and by the physical effort of men working with picks and shovels in the narrow base of an excavation that was, at its worst, a 60-foot vertical cut through unstable Reading beds clay. The cutting opened in 184 years later. Every train on the Great Western Main Line between London Paddington and the west of England passes through it. Every single one. Under this video, you'll see a subscribe button, a small action with a big meaning. By pressing it, you're not only supporting the creation of more content like this, but you're also becoming part of the very exchange we've been talking about, giving and receiving in harmony. It's not about the size of the action, it's about the meaning. A simple subscription tells me these words reached you. It tells me that the effort, the late nights, and the discipline to bring this message forward mattered to someone on the other side of the screen. Like the video, subscribe to the channel, leave a comment below with the name of a structure you would like us to cover next. The Great Western Railway received its Act of Parliament in 1835.
Indeed.
The route Brunel surveyed between London and Bristol was, by the standards of railway building in the 1830s, extraordinarily flat. The Thames Valley offered natural levels that most railway engineers would not have had the luxury of following. Brunel followed them deliberately. His specification for the Great Western was a maximum gradient of 1 in 1,000, far shallower than almost every other main line then being built in Britain. The logic was speed. A locomotive pulling a heavy train on a steep gradient loses speed and burns fuel. A locomotive on a level track at sustained speed moves more freight and more passengers for the same fuel cost. Brunel's railway was not designed for the locomotives of 1835. It was designed for locomotives that did not yet exist. Faster, heavier machines that would benefit from a flat road more than contemporary engines could demonstrate. Sonning Hill sat directly across this philosophy. East of Reading, the terrain rises as the Thames Valley gives way to the higher ground of the Berkshire and Oxfordshire Ridge. The ridge is not dramatic, a few hundred feet of elevation change across several miles. On a road, it is barely noticeable. On a railway built to Brunel's gradient specification, it was an obstacle that required a decision. The options were a deviation around the hill, adding miles to the route, a gradient that would compromise the line's performance specification, or a cutting that would remove the hill from the equation entirely. Brunel chose the cutting. 2 miles long, 60 feet deep at the maximum point, 3 million cubic yards of material to be removed before a single train could run. The geology of Sonning Hill compounded every difficulty. The Reading beds, the geological formation through which the cutting passes, are a mixture of clay, sand, and gravel laid down in the Eocene period, approximately 55 million years ago. The clay component is expansive. It absorbs water and swells, then dries and contracts, repeatedly and predictably, with the seasons. A cutting face in Reading beds clay does not remain stable after excavation in the way that a chalk or sandstone face would. It creeps, it slips under saturation. The sides of a deep cutting through this material require constant management. Drainage channels cut into the slopes to remove surface water before it reaches the clay body, slope angles shallow enough to reduce the stress on the cutting face, and in places, brick retainers and pitched stone facing where the slope geometry alone was insufficient to hold the ground against the pressure of the swelling material behind it. Brunel's team surveyed the material in the trial borings taken before construction began. They understood what they were cutting through. The drainage specification for Sonning cutting was not the standard railway earthwork drainage applied to chalk or gravel cuttings elsewhere on the Great Western. It was designed specifically for the behavior of Reading beds clay under the particular rainfall and temperature conditions of the Berkshire Ridge, and it was built to a standard that has maintained the cutting sides in stable, operational condition for 184 years without reconstruction of the slopes themselves. The workforce at Sonning was approximately 3,000 men at peak, drawn from the pool of itinerant navvies that moved from contract to contract across the expanding British railway network in the late 1830s. These were men who had built the earlier canals and who now applied the same methods, the same picks, the same barrows, the same inclined timber runs to railway earthworks on a scale that the canal era had not required. They worked in the base of the cutting as it deepened, removing spoil in wooden barrows pushed up inclined timber planks to the surface, where horse teams hauled the material away in carts to form the embankments at either end of the section. The work was entirely manual, from the first blow of the pick to the last cartload of spoil. There were no steam excavators on the Sonning contract. No mechanical equipment of any kind moved the 3 million cubic yards of Reading Beds material that had to come out before the first train could pass. Men with picks loosened it. Men with shovels loaded it into barrows. Men with barrows pushed it up runs that became progressively longer and steeper as the cutting deepened toward its 60-foot maximum. By the time the cutting reached full depth, a navvy pushing a loaded barrow from the floor to the surface was climbing the equivalent of a 6-story building on a narrow plank, in all weather conditions, multiple times per working day. The Great Western Railway's records list the construction cost of the Sonning section as £187,000. It does not list the names of the men who earned it. On Christmas Eve 1839, a section of the cutting's north face collapsed after several weeks of heavy rainfall had saturated the Reading Bed's clay to the point at which the slope could no longer support its own weight. The slip was substantial, several thousand cubic yards of material descending onto the partially completed track bed, burying a section of the formation and blocking the cutting for the weeks that followed. The men who had spent months removing material from the cutting floor returned after Christmas to find it partially refilled by what the hill had returned. It was not a failure of construction method or engineering judgment. It was the Reading Bed's clay behaving under extreme saturation in precisely the way that Brunel's survey had indicated it would under the worst conditions. The question was not whether it had happened, but how to prevent it from happening again once the line was operational. Brunel's response addressed both problems together. The failed slope was recut to a shallower angle in the affected section. The drainage works, which had been progressing alongside the excavation, were accelerated and extended. Additional drainage channels were cut into the slope face above the slip zone to intercept rainfall before it reached the clay body. The face was stabilized, the track bed was restored, and the cutting opened on 1 March 1840, 4 months after the slip, carrying the first trains on the Great Western Main Line through the hill that Brunel had decided, 4 years earlier, his railway would not climb. The cutting sides today are managed by Network Rail under a program of ongoing drainage maintenance and slope monitoring that has its origins in the drainage specification Brunel established in 1839. The Reading Bed's clay still behaves as it did when the navvies first cut into it. It still absorbs water and swells. It still requires drainage to prevent saturation of the cutting faces. The difference between a stable cutting and an unstable one, in this geology, is almost entirely a matter of drainage. Brunel specified the drainage correctly. Network Rail has maintained it. The cutting that 3,000 men dug by hand in 26 months has required no fundamental reconstruction in 184 years of continuous mainline use. Every train between London, Paddington and the west of England passes through Sonning cutting. High-speed passenger trains, heavy aggregate freight, engineering trains, maintaining the track at night, the Class 800 intercity, express trains that now operate the Great Western Main Line are significantly heavier and run at higher speeds than anything Brunel's gradient specification was designed to accommodate. The technology has changed beyond recognition in 184 years. They pass through the cutting at up to 125 miles per hour, 60 feet below the surface of the hill that Brunel refused to negotiate with in 1836. The cutting walls, faced in brick where the clay required physical support and left as grassed earthwork where the slope geometry was sufficient, look from a passing train window like a feature that has always been there. They have been there long enough that passengers have no reason to consider them a construction. The hill is simply absent from the journey. That is the complete achievement of Sonning cutting. Not that it can be seen, but that it cannot be noticed. A project of this scale today would be assessed against alternatives before a single cubic yard was moved. Tunneling technology, gradient relaxation, route deviation, each would be costed and modeled. The cutting solution, gradient relaxation, route deviation, each would be costed and modeled. The cutting solution might still be selected, but the procurement process, environmental assessment, and planning consent required before construction could begin would extend the program by years. The cost, at modern civil engineering rates, 3 million cubic yards of excavation, would run to hundreds of millions of pounds. There would be pressure throughout to find a cheaper approach, a steeper gradient here, a shorter cut there, and the result would be a railway that performed less well for the entire duration of its service life. Brunel's answer was to do it properly, once, and to build the drainage that would keep it stable indefinitely. 3,000 men with picks and wheelbarrows, 2 miles, 60 feet, 184 years. Here again you see a megastructure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.